Transitioning to group data and class intervals. Welcome, everyone. Today, we are going to explore a vital transition in our study of statistics, moving from simple lists of numbers to something much more organized. Up until now, in our previous lessons, we have primarily dealt with what we call ungrouped data. This is a type of data where every single observation or measurement is listed individually, one by one. While this works fine for small sets, it becomes quite difficult when we look at real-world scenarios. Think about it this way. Imagine a school principal who wants to analyze the mathematics exam marks of 1,000 students. If they were to simply list every single mark from the first student to the 1,000th, they would end up with a massive, overwhelming, and frankly, very confusing list of numbers. It would be nearly impossible to see the big picture just by looking at a wall of individual digits. To solve this problem and make such large datasets manageable and meaningful, we use a technique called grouping the data. We condense that long list into what we call grouped data. Instead of looking at every single point, we organize these individual observations into specific groups, which we refer to as class intervals. By doing this, we shift our focus. Instead of getting lost in every single individual value, we can clearly see the overall distribution of the data, allowing us to understand patterns, such as how many students scored in a certain range, rather than just seeing a sea of random numbers. In the next slide, we will look closer at exactly how these class intervals are structured. Understanding class intervals. Think of a class interval as a container or a specific range of values that allows us to group different observations together. To make this clearer, let's look at the difference in how we present information. In our previous lesson on ungrouped data, we might have listed specific scores like saying, 3 students scored 41, 43, and 47. That's a lot of individual numbers to track, but with grouped data, we can simplify that entire sentence to say, 3 students scored between 40 and 50. See how much cleaner that sounds. We've traded individual points for a single, manageable range. Now, to use this method accurately, you need to understand the 3 key components that make up any class interval. Let's use the interval 10 to 25 as our example. First, we have the lower class limit. This is simply the smallest value that can belong to that specific group. In our example of 10 to 25, the lower limit is 10. Second, we have the upper class limit. This is the largest value that can belong to the interval. For our example, the upper limit is 25. Finally, we have the class size, which you might also hear referred to as the width of the interval. To find this, you simply calculate the difference between the upper limit and the lower limit. Mathematically, we express this as class size equals upper limit minus lower limit. So, for our interval of 10 to 25, the calculation would be 25 minus 10, which gives us a class size of 15. Now that we understand why we need to move away from listing every single number individually, let's dive into the actual mechanics of how we do this by looking at class intervals. Understanding these components is crucial, because in the next slide, I'm going to show you a very specific rule about what happens when a number lands exactly on that upper limit. The convention of upper class limits. Now that we understand the components of a class interval, we need to address a very important rule. When we transition from a simple list of numbers to group data, we face a specific challenge: deciding exactly where to place a value that falls precisely on the boundary between 2 intervals. Here is the rule you must memorize. In a continuous frequency distribution, if an observation coincides exactly with the upper class limit, we do not leave it in the current group. Instead, we count it in the next, or higher, class interval. Let me give you a concrete example to make this clear. Suppose we are looking at 2 consecutive intervals, interval A, which is 25 to 40, and interval B, which is 40 to 55. If we encounter a data point with the exact value of 40, where does it go? Following our rule, it will not be placed in interval A, the 25 to 40 group. Instead, it will be moved forward and placed into interval B, the 40 to 55 group. Keep this rule in mind, because as we move into our next slide, you will see me apply this exact logic to organize a set of student heights into a frequency table. Real-world example, organizing student heights. Now that we understand the theory behind class intervals and that very important rule regarding upper limits, let's put everything we've learned into practice with a real-world example. Imagine a teacher is measuring the heights of a group of students in centimeters. If we look at the raw, ungrouped data, just like the messy lists we discussed in the first slide, we have these values: 152, 158, 160, 165, 160, 172, 175, 180, 185, and 170. To make sense of this, the teacher decides to group this data into class intervals of 10 centimeters each, starting our first group at 150. Let's walk through the step-by-step grouping process together. First, we need to define our class intervals. Looking at the range of our heights, we can create 4 distinct groups: 150 to 160, 160 to 170, 170 to 180, and finally, 180 to 190. Now, for step 2, we assign each individual observation to these intervals. This is where we must be very careful to apply the convention we just studied in the previous slide. Let's look at the first group. The values 152 and 158 both fall clearly between 150 and 160, so they belong to the first interval. Next, we encounter the value 160. Now, remember our rule: since 160 is the upper limit of our first interval, it cannot stay there. It must move to the next higher class. So, 160 moves into the 160 to 170 interval. Continuing through the list, we see 165 and another 160. Both of these fit perfectly into that second interval, the 160 to 170 group. Moving further up, we have 172, 175, and the value 170 itself. Just like before, because 170 is a boundary value, it moves up, placing all 3 of these values into the 170 to 180 interval. Finally, we have 180 and 185. Since 180 is the upper limit of the previous group, it shifts into our final interval, the 180 to 190 group, along with 185. By following this systematic approach, we have successfully transformed a random list of numbers into organized groups, which we will now summarize in a formal frequency distribution table on the next slide. Frequency distribution table. Now that we have walked through the step-by-step process of sorting our raw data, let's take a look at the final result presented in this frequency distribution table. This table is the culmination of everything we just discussed. Looking at the first column, which represents our height interval in centimeters, we see our organized ranges. Starting from 150 to 160, then 160 to 170, followed by 170 to 180, and finally 180 to 190. In the middle column, we have the tally marks. This is where we physically recorded each observation as we sorted them. For the first interval, you can see 2 vertical marks, and for the last interval, we also have 2 marks. For our middle 2 intervals, you'll notice 3 marks each. Finally, the third column shows the frequency, denoted as f sub I. This is simply the numerical count of how many students fall into each range. So, for the interval of 150 to 160, the frequency is 2. For the next 2 intervals, the frequency is 3 each, and for the final interval, the frequency is 2. By looking at this table, you can immediately see the distribution of heights at a glance, which was much harder to do when we were just looking at that long, unorganized list of numbers from the previous slide. In our next slide, I will highlight some common pitfalls to watch out for when you are constructing these tables yourself. Common mistakes to avoid. First, let's talk about misplacing boundary values. This is, by far, the most frequent mistake students make. As we discussed in the previous slide with our height example, if you have a value that falls exactly on the boundary, such as 40, do not place it in the interval from 25 to 40. You must always remember this rule. The upper limit moves to the next class. Second, be careful with overlapping intervals. Consistency is key to a good frequency distribution. If you have started your pattern with intervals like 10 to 20 and then 20 to 30, you must maintain that same class size. Do not suddenly switch your pattern to something like 25 to 35, as this breaks the continuity of your data. Finally, watch out for ignoring gaps. In some datasets, you might encounter what we call inclusive intervals, where you see ranges like 10 to 19 and then 20 to 29. These are structurally different from the exclusive intervals we have been practicing, such as 10 to 20 and 20 to 30. I want to emphasize that the convention we have learned today, where the upper limit moves to the next group, applies specifically to these exclusive or continuous intervals. This is the standard method you will be using for calculating the mean in grade 10. Now, before we wrap up and look at our final summary, I want to pause and discuss some common pitfalls. Even if you understand the concept, it is very easy to make small errors when organizing your data. Keep these points in mind, and you will avoid the most common errors in statistical grouping. Key takeaways. First, remember that group data is our primary tool for simplifying large, overwhelming datasets. Instead of looking at a massive, unorganized list of individual numbers, we organize them into manageable ranges, which makes the data much easier to interpret. Second, we learned how to define a class interval. Every interval is composed of two essential parts: the lower class limit, which is the starting point, and the upper class limit, which is the end point of that specific range. Third, and perhaps most importantly, we covered the boundary rule. This is that crucial convention we discussed earlier. If you encounter a value that is exactly equal to the upper limit of a class, you must not include it in that current group. Instead, you always move it into the subsequent, or higher, class interval. Finally, keep in mind the ultimate goal of this entire process. By applying these rules, we transform a raw, chaotic list of numbers into a structured frequency distribution table. This organized format is what allows us to perform much more complex and meaningful statistical calculations with ease. All right, we have reached the end of our lesson, so let's take a moment to recap the key takeaways from today's session to ensure everything is clear. I hope this summary helps solidify your understanding. If you have any questions about these points, please feel free to ask.